Hi, this is Harshit Padni, roll number 201501101107, and this is the second video in the series on irreversibility and heat generation in the computing process. Information processing is inevitably accompanied by a certain minimum amount of heat generation. The simplest way of anticipating our conclusion is to note that a binary device must have at least one degree of freedom associated with that information. Classically, a degree of freedom is associated with kT thermal energy. Any switch in signals passing between devices must therefore have this much energy to override the noise. In this paper, we studied two simple yet representative models of bistable devices to yield the relationship between speed and energy dissipation, and to estimate the effects of errors induced by thermal fluctuations. Main conclusion, which has subsequently become known as lauderers principle, is that the erasure of information as some computational device is necessarily accompanied by an appropriate increase in the thermodynamic entropy of the device or its environment. This result is often generalized as follows. A. Any logical irreversible process must result in an entropy increase in the non-information bearing degrees of freedom of the information processing system or its environment. B. Any logical reversible process can be implemented thermodynamically reversibly. For example, the paper of Charles Burnett in 2003. These two statements are believed to provide the sought after link between thermodynamics and computation. A device is called logically irreversible if the output of a device does not uniquely define the inputs. We believe that devices exhibiting logical irreversibility are essential to computing. Logical irreversibility, we believe, in turn implies physical irreversibility, and the latter is accompanied by dissipative effects. The arguments for logical irreversibility are on three different levels. First argument, machines do depend on logical irreversible states. Second level argument, here we permit only those devices using logical functions of only one or two variables. Third level argument, we permit more general devices like a 3-bit computer. Thermodynamic irreversibility, on the other hand, is a feature of physical processes described by the second law of thermodynamics. There is much controversy about the correct formulation of the latter and about how it can be justified on the basis of statistical mechanics. The information bearing degrees of freedom of a computer interact with the thermal reservoir represented by the remaining degrees of freedom. This interaction plays two roles. First of all, it acts as a sink for the energy dissipation involved in the computation. This energy dissipation has an unavoidable minimum arising from the fact that the computer performs irreversible operations. Secondly, the interaction acts as a source of noise causing errors. In particular, thermal fluctuations give us supposedly switch element a small probability of remaining in its initial state even after switching force has been applied for a long time. It is shown in terms of two simple models that this source of error is dominated by one of the two error sources. Number 1. Incomplete switching due to inadequate time allowed for switching. Number 2. Decay of stored information due to thermal fluctuations. It is, of course, apparent that both the thermal noise and the requirements for energy dissipation are on a scale which is entirely negligible in present-day computer components. The dissipation, as calculated, however, is an absolute minimum. Actual devices which are far from minimal in size and operate at high speeds will be likely to require a much larger energy dissipation to serve the purpose of erasing the unnecessary details of the computer's past history.